Hello, welcome everyone. In today's lecture, we are going to look at a new method to find out displacements in structures. So in the last couple of lectures, we looked at how to use the equivalence between the strain energy and the work done to calculate the displacements and rotations at different points. But we also discussed that that particular method has certain limitations. So Castigliano's theorem is a more general method. It's a more powerful method that can be used in a much more broader variety of circumstances. So that is what we are going to learn today. So the objectives of the lecture is twofold. First, at the end of the lecture, you will be able to state what Castigliano's second theorem is, and then you will be able to apply Castigliano's second theorem for calculating the deflection of beams. Okay? So what is Castigliano's second theorem? The first thing that I want to tell you is that this particular method applies to bodies that are linear elastic and at constant temperature. So for example, if the body has a nonlinear behavior or if the temperature is changing during the deformation, then this method doesn't apply. So what does this theorem actually state? The theorem actually states that the displacement delta J at a point is equal to the first partial derivative of the strain energy in the body with respect to the force Pj acting at that point in the direction of delta J. Or in mathematical terms, delta J is del Ui by del Pj. Okay. So again, it looks very simple, but there are lots of important things that you have noticed here. Okay. The first thing that you have noticed is that the displacement delta J is in the same direction as the direction of the force Pj. Okay, so the delta J, the displacement, and the force have to be in the same direction. Okay, and this derivative del Ui by del Pj essentially gives the displacement of the point in the body with respect to in the same direction as Pj. Okay, so that is something that is very important. Okay, if you want to find out what the displacement is in some other direction, then you have to apply a force in that particular direction. Okay? And the second thing is that the displacement is calculated at the point where the force is being applied. Okay? Not at a different point. So for example, if you have a structure like this, say the force is being applied here, then when you take the derivative of the strain energy with respect to P, you find out the displacement at this point in the direction of P, not at some other point. Okay, if you are at some other point, then the force has to be applied there. So the displacement is calculated at the point of application of the force in the direction of the applied force. Okay. Now, when I say force, it doesn't have to be just a force, it can be a moment. So in the case of a moment, instead of finding out the displacement, you will find out the rotation. So we discussed this in the previous lectures. The force and displacement are complementary variables. Similarly, the moment and rotation are complementary variables. Similarly, the torque and the angle of twist are complementary variables. So essentially, this method can be used to find out not just displacement, but also rotations and angle of twist. It is just that in that case, you have to take the derivative with respect to a moment or a torque instead of a force. Okay. Now, this is Castigliano's second theorem, and this is what we will be using very commonly in analyzing structures. There is also what is called as the Castigliano's first theorem, which is essentially complementary to the second theorem. So that theorem essentially says that the force at a point, Pj, is the derivative of Ui with respect to the displacement at that point, d delta j. Okay, so it's del Ui by del d delta j is Pj. Okay, again, this statement is correct. This is a true theorem, but it is not useful practically because in this case, what you need to know is the deformation field delta j. Okay, so usually that is not known. So it is hard to find out what the forces are by taking the derivative of the strain energy with respect to delta. Okay, so in most of the problems, what you will know is what are the forces or the moments that are being applied, and it is easier to apply the second theorem to find out the displacements. The inverse problem is usually not that trivial. And most of the cases, you don't know what the displacement field is. So you can't find out the forces. Okay. So how are we actually going to apply this? Okay. Now, one of the things that we talked about when we initially talked about energy methods is that if you want to use the equivalence between the strain energy and the work done, then the force has to apply at the point where you're trying to find out the displacement. What if there is no force acting at the point where you're trying to find out the displacement? Okay? In that case, you can still use Castigliano's theorem. What you end up doing in that case is that you assume a dummy or a fictitious load to be acting at that point where you want to find the displacement, and essentially you can take the derivative of the strain energy with respect to that fictitious force. Okay? So let's just look at a simple example. Say you have a cantilever beam, okay? And then say you have a 500 Newton force, okay, acting at the tip of the cantilever beam, okay? But you're not interested in finding out what the displacement at the tip is, but rather you want to find out what the displacement at some point in the interior of the beam is. Okay, say let's say that this point is 400 millimeters, whereas the whole length is 600 millimeters. So in those cases, what you do is, even though there is no actual force acting at this point, you will assume that there is a fictitious force P acting at that point. Okay? So then what you do is, you find out what is the total strain energy in this cantilever due to this applied load of 500 newtons and also this fictitious load of P, and you take the derivative of that strain energy U with respect to del P, and that will still give you the delta at 400 millimeters. Okay? Again, this might look a little bit abstract right now, but when you do a problem, it will become kind of obvious. Okay? So the main advantage of this method is that you can use this dummy loads. It could be a dummy force or a dummy moment or a dummy torque to essentially calculate the displacement or the rotation or the angle of twist at any point in the structure. Okay, so that is why this method is very powerful. Okay, now let's look at a very specific example. Okay, I told you that delta is del U over del P. Okay, so what does that actually mean for specific cases? Okay, let's say that you have only a pure bending deformation on the beam. We know that the bending energy is actually given by integral from 0 to L m squared dx by 2EI. Okay, so essentially you have to take the derivative of this integral with respect to P, or more precisely you have to take the partial derivative of this integral with respect to P. Okay, so when you have to take a partial derivative of an integral, in some cases you can actually take the derivative inside the integral. So the del over del P of integral 0 to L m squared dx by 2EI essentially become the integral from 0 to L of del by del P of m squared by 2EI times dx. Okay. Now the derivative of m squared dx is nothing but 2m del m by del P. Okay. So that 2 here and this 2 here cancel off. So essentially you end up with an expression where delta is given by the integral from 0 to L of m over EI del m over del P times dx. Okay? So m is the moment function. M is the internal moment function of the structure, and you essentially perform this integral from 0 to L, which is the length of the beam. Okay? So delta is the displacement of the point caused by the actual loads acting on the body. Okay, so this is something that is important. So you assume a dummy load in case there is no actual load acting at the point, but then the displacement that you calculate is still the actual displacement, not a fictitious displacement. Okay, this P, okay, is essentially an external force of variable magnitude acting at the point in the direction of delta. So essentially you have to take the derivative of U with respect to P. So essentially in that case, P has to be a variable force or a variable moment or a variable torque. Okay? And in this particular case where you're looking at only bending deformation, this M is nothing but the internal moment acting in the body caused by the fictitious force P as well as the actual loads. The actual loads can be both forces and moments. Okay? So the M that we calculate, that we put inside the integral, is caused by the actual loads as well as the fictitious load that you are applying. Okay? Now, we can also find out what the rotation or slope at a point by using the complementary formula. So since delta is del u over del p, theta is del u over del m prime, where m prime is the variable couple moment acting at that point. Okay, so you can think of an example like this. Okay, say you have again some force, of say 500 newtons acting there, and say you want to find out the rotation at this point. Okay, so what you do is you assume a dummy moment m prime acting at that point, find out the internal strain energy due to m prime as well as this 500 Newton force, and take the derivative of that strain energy with respect to m prime. So that is this del u over del m prime. Okay, so in terms of the actual strain energy equation, again there's only bending in this case, so that turns out to be like this. So the bending energy is integral 0 to L m square dx over 2ei. Okay, so when you take del u bending over del m prime, that essentially becomes the integral of 0 to L del over del m prime times m squared by ei, or m squared by 2ei times dx, and that essentially turns out to be integral from 0 to L m times del m over del m prime dx over ei. Okay, and that is what we have here. Okay, so essentially the expression for theta is very similar to the expression for delta, except that in this case you take the derivative with respect to m prime rather than the derivative with respect to p. Okay. Another thing that I want to point out is that this p and m, or p and m prime, all these things are concentrated forces or concentrated moments. Okay, so in this case sometimes this m prime is also called a couple moment, and sometimes it's also called a concentrated moment. It's essentially the same thing. Okay. Now, in this case, both the cases that we looked at, we had only pure bending deformation. Okay. On the other hand, you could have a structure that is subjected to bending, torsion, and axial deformation. So in those cases, what you essentially have to do is find out the internal strain energy due to all these modes of deformation, bending, torsion, and axial deformation, and then take the derivative with respect to either p to get the displacement, or with respect to m prime to get the rotation, or with respect to t prime to find out phi, which is the angle of twist. Okay, so we will look at multiple examples of using Castigliano's theorem, and each case will be a little bit different, so that you explore a fair variety of problems in how to use Castigliano's theorem. Okay, so now we'll start with something that is actually very, very simple. Okay, so this is a cantilever beam that is subjected to a uniform load of intensity W. Okay, W is typically in newtons per meter or pounds per meter, okay, or pounds per inch, depending on which units you are in. Okay, so it is not a force; it's a force per unit length. Okay, so in this case, you have a beam that is subjected to a force per unit length W, and the length of the beam is L. We are asked to find out what is the displacement at this tip B, okay, using Castigliano's second theorem. And we are also given that the bending rigidity of the beam is E times I. E is the Young's modulus, and I is the area moment of inertia. Okay. Now, this is a simple case where there is actually no concentrated force acting at point B. Okay. This force per unit length W is uniformly distributed across the entire length, but there is no concentrated force acting at point B. And we have to take the derivative of the strain energy with respect to a concentrated force to find the displacement at point B, which means that we essentially have to use a fictitious force. Okay, so what I'm going to do is I'm going to assume that there is a fictitious force P that is acting at point B. Okay? Now, if there is a fictitious force acting at point P, then I can take a section somewhere like this, and that is how my free body diagram will look like. Okay? If you look at the free body diagram, there has to be a shear V, and there has to be an internal moment mz, which is my moment m. Okay? Now, you can use the equilibrium of forces, sigma Fy equal to 0, to find out what this V of x is. V of x turns out to be P, which is the concentrated force, or the assumed concentrated force at point B, and the contribution due to the distributed load is W times x, where x is the total distance of that section from the point B. Okay, this is again something that you have learned multiple times in your solid mechanics class and also in this class, so you should be quite comfortable writing down these equations. Okay. Similarly, we can also find the moment equation. So in this case, there is going to be a moment due to this internal moment. There is going to be a moment due to the shear V, and there is also going to be a moment due to this W. Okay, so if you take moment about this point, these three forces, or the two forces W and V, will contribute, and also you will have an internal moment. So you write what is the equation for m of x, and the equation for m of x turns out to be something like this. Okay, it is minus px minus wx squared over 2. Okay, now once we know the moment function m, then finding delta is actually quite trivial. So essentially we have to put this moment function into the equation for bending energy, which is m squared over 2ei times dx, and take the derivative with respect to p. That I have already done here. So delta is 0 to L m over ei del m over del p times dx. Okay. Now, one thing that I want to point out is that this derivative is taken with respect to p, not with respect to x. Okay. So this is my moment function minus px minus wx squared over 2, and I'm now taking the derivative with respect to p, which means that the derivative of this term is going to be equal to 0 because it doesn't have a p term in it. Okay, so del m over del p is going to be minus x. Okay, not something else. So this is a point where a lot of students make mistakes. So make sure that you take the derivative with respect to the force p, not x. Okay, so del m over del p is minus x. Okay, so essentially you can take this and put it into that equation. M is already known, which is that. So essentially you populate the integral, and then you take integrate the function, and then you put on the limits. Okay, so this is your del m over del p, and this is your m. I have taken at the ei out of the integral. Okay, so if you do the calculation, you will find out what the delta is. Now, at this point, after you have taken the derivative with respect to p, we can essentially put p equal to 0 because p is a dummy force. It was not there in the actual problem. It is something that we assume. So essentially, p equal to 0. Okay. So now once you've already taken the derivative of the strain energy with respect to p, we can essentially substitute p equal to 0 into the equation. So essentially, if you look at this, this term is 0. Okay, so we just have to integrate minus wx squared over 2 times minus x dx from 0 to L. And if you do that, this is what you get. Okay, so essentially the delta is given by w L to the 4 divided by 8ei. So if you look at this expression, there is no p because p was a fictitious moment or a dummy fictitious force or a dummy force that we assume. The delta depends only on the actual load that is being applied, which is W. And of course, it depends on the length of the beam and the cross section and the material properties. Okay? But it doesn't have the P term. Okay? So this is how we find the deflection at a point. So in the next lecture, we'll look at examples where we find the rotations and look at cases where there are multiple forces or multiple moments and so on. Okay? With that, I'll conclude this lecture, and I'll see you next time.